So this is exercise 7.2, and here we're looking at a model of a water tank. So we have the tank here, and the height of water in the tank is denoted by h. The inflow to the tank is x, and the outflow from the tank is v. And this inflow to the tank is determined by the valve here, so that's something you can open and close to control the amount of water, x, that is going into the tank. And the exercise says that we have a guy called Stu Dent, a funny name. He's got the assignment to keep the water level in the tank constant in spite of variations in the outflow Vt. And it's also being said up here that all variables denotes offsets from an operation point. So what this means is that he wants the water level to be 0. There's some certain level here that's in this operation point is chosen to be the 0 level. So that's what we want. Anything below that level is regarded as being a negative value, and anything above is positive. And then we get some information here that Stu determines the transfer function GVOS from the valve to x of t. So we know the relation between x and the valve opening. And by step response experiments he obtains the following result. So we know exactly what that transfer function is. It's a first order transfer function looking like this, 1 on 0.5 s plus 1. So first we have the A exercise. It says because the disturbance Vt is measurable, so we can measure the outflow. That's what that means. Stu is first considering a feed-forward compensator to completely eliminate it. So he designs this one. Stu, who also knows that it's dangerous to differentiate the disturbance, cancel all the derivative terms in the compensator. Determine the response h of t Stu will get if the outflow v of t is changed stepwise with an amplitude of 0.1. Alright. The first thing we need to do is to find the relation that relates x and h and v to each other. So h is the height in the tank, x is the inflow, and v is the outflow. So we'll need to use mass balance. So what is that? Well, if we look at the inflow into the tank, x of t, and then if we take that minus the outflow, v of t, so inflow minus outflow, and that of course is equal to the change of the volume in the tank. So volume in minus volume out, and that change is equal to the area of the tank multiplied by the change of the height, h. So a times the h dt is equal to x of t minus v of t. Just mass balance. And now we're going to make an Laplace transformation in this, so we can work with this in the Laplace domain. And then we just have to remember that the Laplace transform of the derivative corresponds to multiplication with s in the Laplace domain. So this left side will transform as a s h of s, and then on the right side of course we have just x of s minus v of s, and of course we can express this as h of s is equal to 1 on a s x of s minus v of s. And then we were given the relation that x of s, the inflow, was related to the valve opening through the transfer function gv of s. So let's call the valve opening u of s. Valve opening like that, which means that if we plug this in there, we get that h of s is equal to 1 on a times s times gv of s times u of s minus v of s. So now in the A exercise we were only supposed to consider the feed forward part here. So this proportional controller is something we can skip now. That doesn't exist in the AX exercise. And up here is the valve, so here is where we have U. Oh, it's marked out there as well, but let's do like this. We have U up there, and then we have a feed forward compensator, so this is a controller, and then we have the outflow V coming here. So what is U? Well, U is just this feed forward controller acting on the output. So let us introduce some notation. So we know that US is the feed forward control. Let us call it capital F, and then we put the lowercase f here to indicate feed forward. So FFOS, and then times the outflow VOS. So if we plug this expression now in here, then we get the final expression here for H of S, which is 1 on AS times GV of S times FF of S times V of S minus V of S. And here we can factor out the V of S, so this becomes 1 on A of S times GV of S times F of F of S minus 1 times V of S, like that. And the task now was to design this feed forward controller such that the water level H becomes independent of the outflow of the tank V. So what we want is this expression to become 0. And we can see here that if we choose if we let this FF of S be equal to 1 on GV of S, then what's going to happen? Well, then we'll get that GV of S times FF of S minus 1 will be equal to GV of S times 1 on GV of S minus 1, which is equal to 1 GV of S on GV of S, 1 minus 1, which is equal to 0. So this choice for FOS would be the ideal one in order to obtain what we want. Then the output level would be completely independent of the outflow V of S. So So ideally we want F of F to be equal to just what we wrote, 1 on GV of S, which is what? Well, we knew that GV of S was equal to 1 on 0.5 S plus 1, so the inverse of that is simply 0.5 S plus 1, right? But now the thing was that we had this part in the exercise that said, Stu, who also knows that it is dangerous to differentiate the disturbance, cancel all the derivative terms in the compensator. And the reason is that it's dangerous to differentiate it is that if the outflow, the water level, changes very rapidly, then the derivative becomes very large, and that means that we may have to use very, very large input values, in theory infinitely large, and of course that's not possible in a practical system. So when it says cancels all the derivative terms in the compensator, that means that we should cancel all the terms that involves just a multiplication with s, because multiplication with s is the Laplace transform of a derivative. So we should cancel this term. So I can write this. Cancel derivative terms. Then we get that f of s will be equal to just 1. So it's a constant compensator. So the expression we get for h of s with this choice is 1 on a times s. If you compare with expression we had there, 1 on a times s times gv of s times 1 minus 1 times v of s. Now we can plug in the expression for gv of s. So this is 1 on 8 times s times 1 on 0.5 s plus 1 minus 1, and then times v of s. And let us simplify this expression. So we're going to put this in a common fraction. So we just multiply this 1 with the denominator here, up and down. That will give us 1 on 0.5s plus 1, and then minus 0.5s plus 1 on 0.5s plus 1 times v of s. And this becomes 1 minus 1, which is 0. Then we'll have minus 0.5s on 0.5s plus 1. And then we'll have an s up here in the numerator, and then one s as a factor here in the denominator, and they're going to cancel. So we'll just get minus 1 on a, because we have the minus sign. And then we can multiply this expression with 2 to get rid of these decimals. And then we're just going to get a 1 up here and a 1 here, and then this 1 is going to turn into a 2. So minus 1 on a times 1 on s plus 2. Oops, you didn't see anything of this, I'm sorry. Sometimes forget where I get the borders, but yeah, you have what I say, and you could just verify that this is true if you if you want to. By the way, I forgot to include the v of s terms here. And now the task was to determine h of s, or h of t in the time domain rather, when the outflow v of s was a step function with amplitude 0.1. So what does that mean? Well, that means that we have in the Laplace domain a function that is 0.1 on s, since 1 on s is the Laplace transform of a step, and the amplitude was supposed to be 0.1. So then we get h of s being equal to minus 1 on a times 1 on s plus 2 times s, and 0.1 can be included up here. And then if we want to find h of t, we make an inverse Laplace transformation of this expression, minus 1 on a and I think we used this transform before, but we can shake it up. Here's my table. This is one of the standard transforms, and you find it here in your table as number 11. So let's use number 11, and we'll get that this becomes minus 1 on 2a times 0.1 times 1 minus e to the power of minus t on 2. No, sorry, it's not. I can't use the transform myself. It's minus 2t, like that. It's a bit too quick. And we can write this in one more step to make it look a little bit nicer. Let's see, so this is equal to 0.1 on 2, which is 0.05. So this is minus 0.05 on the area A times 1 minus e to the power of minus 2t, like that. So this is the step response for this water level when we use that feed forward compensation without the derivative terms. So if we look at the n value here, I'm doing this a bit carelessly. Remember to write your own solutions more properly on the exams and stuff. But I just write like this: when t goes to infinity. So then this term is going to cancel because we'll have minus infinity in the exponent. So what we'll get is just minus 0.05 on the area A. So we won't obtain what we wanted. We wanted h of t to be equal to 0. And here we have some steady state error. But let's see what we can do next, because in exercise B we're going to try to fix this. So that was the A exercise, but in the B exercise it says this: to improve the control system, Stu also introduces a proportional feedback of the water level H. And what is the steady state error in the level in H now? If we have the same, if we have the same step on the output to be. So this time we have to care about the proportional controller here. So let's call that F. And it's just a proportional controller, so it's equal to a constant gain K. And now we see that the input signal to the valve will become, let's erase this one. So the input signal to the valve, U of S, will now be a sum. So we'll have this contribution and that contribution. So we'll have K times H of S. And then we'll also have the same thing as we had before, V of S. Since this one was equal to 1 after we cancel the derivative terms. So now we can go back to what we had earlier somewhere. Let's see. Yeah, up here even. That expression when we still had no actually it's up here when we still had U of S, and then we just replace U of S here with this. So that will give us H of S is equal to 1 on A times S times GVS times K H of S minus V of S, and then minus V of S, and then parenthesis. And now we want to solve this relation for H of S. So let's do that. So first we just write this out. I can multiply with A times S to get it up here. And on this side we have GVOS times K times H of S minus GVS times v of s, and then minus v of s, like this. And then I will move all terms with h of s over to the left hand side, so that will become h of s times as minus gv of s times k. And then on the left hand side we have the v of s terms, and there we have minus gv of s plus 1 times v of s, like that. And now we can solve this for h of s just by dividing with this. So h of s becomes minus gv of s plus 1 on as minus gv s times k, and then this multiplied with v of s. Oh, by the way, did you notice that I missed a sign here? It should have been a plus sign there, right? Which means that we should have had a plus sign there and a plus sign where? Well, it won't be, it would be like this. gv of s minus 1. Okay. gv of s minus 1 instead. That's a drawback of making video recordings, that you don't have a student correcting you instantly. I'm sorry for that. Hope it didn't confuse you too much. Okay. Let's plug in the expression we had for gv of s, which was 1 on 0.5s plus 1. And then minus 1 here. And as minus 1 on 0.5s plus 1 times k times v of s. And then we're going to continue. Oops. Continue with this. Blah blah. So this becomes what? We multiply numerator and denominator with this thing, so we get rid of the fractions up there and there. So that one will just become a 1, and then this one becomes a 0.5s plus 1. And down here we get as times 0.5s plus 1 minus k times v of s. And what is this? Well, up here we'll have 1 minus 1, and that's going to be 0, and then we'll have minus 0.5 s. And in the numerator we'll get 0.5 times a times s squared plus as minus k times v of s, of course. And then again we were going to consider the case when we have a step on this outflow v of s, so 0.1 on s. So what's going to happen with h of s then? Well, here I'm not going to do any inverse Laplace transformation. We can just use the n-value theorem to find out. So the n-value h of t after a long time is found in the Laplace domain as s times h of s, and then we take the limit when s approaches 0. And that is equal to what? Well, it's equal to the limit and then s, and then we just substitute h of s with this whole thing. So minus 0.5 s on 0.5a s squared plus a of s minus k times v of s, which is 0.1 on s, and then we can cancel this s and that, for instance. And what remains is just this limit for 0.5 s on 0.5 as plus as squared plus as minus k. And since we have s up here in the numerator, this whole thing is going to become 0 when s approaches 0. So that's what we get. And that's good, right? That's what we wanted. So by introducing this proportional controller, we could obtain the limit that was desired, because we wanted to keep the water level constant on this operation point, which we defined as 0. Alright, I guess that's everything with exercise 7.2.